we have these two equations. Change in entropy for the universe is the sum of the change in entropies for the system and the surroundings. Change in entropy for the surroundings is negative delta H of the system over T. So let's put these two equations together and multiply by negative T. So what does that give us? We got delta S for the universe is equal to delta S for the system. And instead of delta S surroundings, I'm going to write this, minus delta H for the system divided by T. And then I'm going to multiply both sides by negative T. So I get negative T delta S for the universe. When I multiply this guy by negative T, it just becomes delta H minus T delta S for this system. So this is the equation we just derived. We're going to drop the cis subscript and just understand that any quantities that don't have subscripts are referring to the system, not to the universe or the surroundings. So negative T delta S for the universe is equal to delta H minus T delta S. The Gibbs free energy is given the symbol G. Thankfully, that one makes sense. Gibbs free energy is equal to H minus Ts. So H is enthalpy, T is temperature in kelvins, S is entropy. So when you take entropy and multiply by temperature, you get energy. So the change in Gibbs free energy at constant temperature is going to be the change in G is going to equal the change in H minus T times the change in S. And as usual with energy, we're interested in the change, not in the absolute amount of energy, because that is what's useful, and the absolute amount of energy is not helpful. So the change in Gibbs free energy occurring at a constant temperature and pressure is proportional to negative T delta S for the universe. Let's go back here. Because this equals negative T delta S for the universe. So they're looking at this part in the next slide. Delta G is proportional to the change in entropy for the universe. So delta G also works as a criteria for spontaneity. Gibbs free energy can be called the chemical potential energy, similar to the mechanical potential energy. And so chemical systems will tend towards lower Gibbs free energy. If delta G is less than 0, it's a spontaneous process. If delta G is greater than 0, it's non-spontaneous. We can calculate delta G just from looking at the system. We need delta H, which was covered back in chapter 7. There's a typo in your printed slides, because they changed the book a little. And delta S is just covered in the previous section. So the Gibbs free energy change determines the direction of spontaneous change. So if we look at this equilibrium here, a mixture of nitrogen and hydrogen gases, at equilibrium, we have Q is equal to K. When Q is smaller than K, we have a spontaneous reaction towards the products. When Q is greater than K, we have a spontaneous reverse reaction, again, towards the products. So this is matching up with what we learned earlier. So Gibbs free energy is a combination of delta H, delta S, and T. And so if we're going to look at spontaneity, we can look at the effects of these three different things. So there's different cases. So case one, we've got negative delta H and positive delta S. So an exothermic reaction has a negative delta H. It's releasing energy into the surroundings. And if we have a positive change in entropy, the reaction will be spontaneous at all temperatures. Because this is negative, and because this is positive, and we're subtracting that, delta G has to be negative at all temperatures. So this will be a spontaneous process. If delta H is positive and delta S is negative, an endothermic reaction with a negative change in entropy, the reaction is non-spontaneous. Because here this is positive, and because this one's negative, this always is going to end up being positive. And so it doesn't matter what the temperature is, this is not a spontaneous reaction. If delta H is negative and delta S is negative, well, this is negative, so this is contributing to a spontaneous reaction. But if this is negative, this term becomes positive, and so this is working against it. And so now the spontaneity will depend on the temperature. If temperature is large, then this positive term is going to win. And if this is small, the negative term wins. So we get spontaneity at low temperatures and non-spontaneity at high temperatures. And then we have the opposite. Well, is that the opposite? Yeah, it is the opposite. Where delta H and delta S are both positive. And now we have the reverse effect of temperature. Bless you. We get non-spontaneous at low temperature, spontaneous at high temperature. So when delta H and delta S have the same sign, the spontaneity will depend on the temperature. So here's a table summarizing that. So here, when they both have the same sign, it's going to depend on the temperature. Spontaneous or non-spontaneous is going to change with the temperature. If these are opposite in sign, it's going to be the same regardless of temperature. You can figure out where that tipping point for the temperature between spontaneous and not spontaneous is by setting delta G equal to 0. That's where it changes from positive to negative. And then you can calculate the temperature at which this would become spontaneous or non-spontaneous. So consider this reaction, calculate delta G at 25 degrees Celsius, and determine whether the reaction is spontaneous. Does delta G become more negative or more positive as the temperature increases? So we're given the information that we need. We need delta H and delta S. And so the Gibbs free energy, delta G, is equal to delta H minus T delta S. So delta H is negative 137.5 kilojoules. Got to convert that. 10 to the 3 joules. Minus the temperature in Kelvin, 25 plus 273 is 298 Kelvin, times the entropy, change in entropy, 120.5 joules per Kelvin. And we see that those kelvins cancel out. That's a really big number in joules, so we would probably express that in kilojoules. So that's going to be negative 101.5, 6 kilojoules is delta G. Is it spontaneous? Yeah, it is. It gets a little confusing because delta S being negative says it's not going to be spontaneous, but delta G being negative says it is. How do we keep track of that? Well, delta G is energy, and so in my mind, its sign conventions line up with things like delta H. So delta H, we're releasing energy, and so that would imply that often delta G is negative as well. So is it spontaneous? Yes, it's spontaneous. Did anybody else get this number? Okay, thank you. Is delta G going to become more negative or more positive as the temperature increases? So as the temperature increases, we're subtracting a negative number, right? So this is going to make this term bigger. We're adding bigger and bigger positive numbers to delta G. So does that make it more positive or more negative? More positive. So this becomes more positive as temperature increases. So this will be spontaneous at lower temperatures and not spontaneous at higher temperatures. Any questions?